Okay, hello. In this video, we'll do a quick revision on Young, Modulus, and Hooke's law and strain energy. If you want to know why I look so done, it's because I recorded the whole thing and then the software crashed. Computer problems, eh? Alright, anyway, Young modulus is defined as the ratio of stress to strain. Okay? And Young modulus actually tells you how hard and ductile the material is, wink. So stress here is defined as force per unit area, and strain is defined as extension per unit original length. Okay, so it's a bit like if you want to sub the equation, right, or use the equation. This is the area, and we say stretch a material with a force F, so the material will elongate and become longer. Okay, and we'll take the extension divided by the original length of the material. By the way, if you want a better or a more full, proper explanation, please watch Miss Elizabeth's video. Okay. Anyway, this is the unit for extension and stress. Okay, they are both Pascal, which is also the same for pressure. If you want a PDF export of these notes, check the description. It will be down there. So we are very familiar with Hooke's law, at least I hope you are, which is a graph or a situation where the force applied on the material is directly proportional to the extension. So you kind of like must get a straight line that passes the origin. Okay? So that is the statement of Hooke's law, where the force acting on the material is directly proportional to the extension of the material. Okay, so F is equal to Kx. And another thing about this is that if you want to find the strain energy, you would look for the area under the graph. Sometimes we also call it elastic potential energy. So area under graph can be calculated using half Fx or half Kx squared. Okay? So sometimes, right, we do encounter situations where Hooke's law is not applicable, or there is some form of permanent extension going on. Okay? By the way, right, this graph got points, got name one, okay? Please go study. So this one is the extension, okay? And this one is when you remove the force. So maybe you stretch a material like plastic or rubber, and then after you remove the force, it cannot return back to the original length. So this yellow color shading shows you the energy I use to stretch the material, which is also the energy stored inside the material. Okay, energy stored inside the material. But when you remove the force, right, you don't get back the energy, because this green color is the energy that is returned back to the system. So for example, if you stretch a rubber band and the rubber band shoots off into the distance, that energy is returned in the form of Ke. So because the energy stored and the energy returned is not the same, this shaded area is actually the energy lost to heat. Okay, again, objective can ask. So in this question, it says that one end of a spring is fixed on the support and the mass is attached on the other end, and the mass is in equilibrium. Explain what is meant by equilibrium. So what we can say is that the upward tension from the spring is equal to the downward weight of the mass. Okay? So whenever you talk about equilibrium, you need to talk about the type of forces, its respective directions, and the fact that the net force or the resultant force is zero. Okay, so hence the resultant force is zero in equilibrium. Ta-da! So you need to obey the conditions for equilibrium. Alright, the mass is then pulled down and we release it at time t equals 0. So mass is going to like oscillate up and down. Okay, so you're asked to find where the speed is maximum. So to look for maximum speed, what we need to do is actually look at the magnitude of the velocity. But velocity is dsdt. So we're looking at places of maximum gradient if you are more mathematically inclined. I'm not sure what my hand is doing. But anyway, all these blue spots are where the graph is the steepest. Now, if you're not so mathematically inclined, you can think of maximum speed where d changes the most in the same period of time. So if you check every single cm, like for example, the first cm, d change a bit, whereas the second cm, d changes the most at those particular position at the second cm, around here lah, at the second cm. Okay, so at all these points, you can write down the time, but 1 is enough. Don't extra. Alright, so elastic potential energy stored is maximum. You look for maximum extension, maximum compression, and maximum extension. Okay, so all these points are accepted. And if you want to find where the mass is in equilibrium, mass is in equilibrium, right, at when there's no extension. Okay, so no added extension, which is 0. Now, if you find all of, 0 displacement, so you just copy a time from part 1. If you find all of this a bit strange, we will teach you the chapter oscillations before you sit for your AS. No worries. So now what we do is we change the mass and we put different mass, but we plot against the total length of the spring. Okay, not extension, total length. Okay, one thing you should note is always that the original length is 20 cm because that is where the force is 0, or there is no mass, the mass is 0, so there's no force, and you can see it's a straight line. So when you are asked to explain whether the spring obeys Hooke's law, obviously yes, because the increase in length is directly proportional to the weight of the masses, which is used to stretch the spring lah. Okay, so you can see as seen from the graph, which is a straight line, x proportional to f. Maybe you can add the term straight line next time. All right, show that the spring constant is 26. So to find the spring constant, we can use F is equal to kx. So what you actually need to do, right, is actually find that this is actually your extension. So you are extending from 20 cm to 35 cm. So the total extension here is 15 cm. You see the 10 to the negative 2 hiding there? So I'm gonna write that down, k, 20 to 35. So minus, show all the working, you see. So minus 20, alright. Okay, and the force needed to stretch to 35 is 0.4 kg. We need to change this to 0.40 times the gravitational acceleration. Alright, so this is just a issue of substitution. This will finally get you your K, 26.16. Alright. So next, you attach 0.4 kg, calculate the energy stored. Now to find energy stored, one part of the axis have to be extension, and one part of the axis have to be the force used to extend it. So this yellow area is actually the area of your stored energy lah. Okay, so whenever you think about strain energy or energy stored, always find the area where one axis is related to the extension, the other axis is related to the other side is related to the force applied. But then you must convert the 0.4 g to force. Okay, so we're going to use E is equal to half kx squared here. And you got your k 26, you got your x squared. My square went for a walk. Sorry about that, but this answer is correct. Alright, moving on. Same setup, but slightly different spring, which give you a slightly different or very different graph. You can see the axis, they flip it. Why? Just to mess with you, okay? So stay and explain whether it obeys Hooke's law. So in this case, no, because it's not a straight line and your graph is not straight enough. Okay, I apologize about the blinking Microsoft Teams icon. But yeah, next time I will drag the window slightly differently. State the form of energy stored in the spring due to addition of the masses. So there's only one form of energy you can store when you change the length, which is elastic potential energy. Describe how to determine whether the extension of the spring is elastic. Well, because it returns to the original length, it will be elastic. So how do you know if it can return to the original length? You remove the masses law. So what we'll do is we will remove the meshes suspended on the spring. So if it returns to original length, the spring is elastic. Okay, so calculate the work done to extend the spring from 40 to 160 mm. So once again, we need to look for area. Thank goodness this is a straight line. If not, we have to count boxes again. Don't want to do that. I don't want to do that. Alright, so from here, right, what I'm going to do is I will draw an extension. Okay, but before I do anything, again, please consider the mass needs to change to the force applied on the spring by multiplying it with the gravitational acceleration. And we will take this extension and this extension, okay, and you can see you need to find this area. Okay, once again, one side of the area is extension, the other side of the extension, and then the other side is actually the line of the graph. Okay, the two sides is the force applied. Okay, so generally we always look for area between the line and the extension axis. Okay, so calculate the work done. We will use half. Okay, this one is trapezium, so we are going to use sum of the parallel lengths. So I'm going to look at the force when the extension is 40 and when the extension is 160. Okay, this is what I mean by the force side. So this is 70 and this is 145. So what we'll do is we'll take sum of the parallel lengths, 70 plus 145. Don't forget to convert to kg. Don't forget to change this to the weight acting on the spring. So we're going to extend from 40 to 160. So you minus law. 160 minus 40 is 120. Okay. So when you do that, what you will get is 0.021. I know that there's an error there, but well, this is exam lah, normal life. I will correct it later. So this 10 to the power negative 3 is converting from gram to kg, and the 9.81 is converting to the force acting on the spring. Alright, so again, be sure to convert. And if you're asking me why I know, it's because it looks a bit weird, the answer. Alright, so after I corrected that 20 to 120, the final answer would be 127 joules. Alright, so we're gonna move on. By the way, right, generally when you talk about Hooke's law or you want to explain whether it obeys Hooke's law or not, you need to refer to the graph, okay? The graph given is not a straight line. So I just feel a bit insecure, so I want to add that the force due to the masses is not directly proportional to the extension. Alright, next question. Define Young modulus of a material. This is the ratio of stress to strain on the material. Okay, so we're going to squish the rod together. That's why you can find that the extension of the rod is decreasing. Okay, and when you are asked to determine the spring constant, we can use F is equal to Kx lah. Okay, so 150 is the original length. To find the extension, I will need to then draw a line from here And I always tend to take the corner value lah. So from here, the extension will drop from 150 mm all the way to 148 mm, which gives us an extension of 2 mm. So we're going to substitute the 2 mm into the equation of F is equal to Kx. Can use a straight line Hooke's law. So 90 times 10 power 3, 90 kilonewton. Okay, X is 2 mm. I see the mistake now. Don't worry, I will change it later in the video. Okay, so when you substitute, you can find the spring constant 4.5 times 10 to the power of 6. Okay, and you see now you are asked to find the energy stored for force is equal to 90 kilonewton. So energy stored or strain energy can be calculated using the equation half kx squared. Okay, so we have k, and I know it's wrong, don't worry, it will change. Your extension is 2 mm, and this is at this point where I noticed that I make a mistake, so this should be -3, 7. So like doing the actual exam, right, you don't have to delete everything one. Please always double check. You see, even the most seasoned person will make mistakes. Alright, so this is 90 joule. Just press calculator. Okay, so the focus of this question, right, is actually the second part where you are asked to actually draw something else. Okay, so anyway, if you are thinking which shaded area we are looking for, I'm just going to draw a regular old Hooke's law graph, which is F is equal to Kx. This is in case in objective they ask you, oh, which area is a suitable representation of the energy stored? Where are you going to shade? Which triangle, trapezium, what on earth? Okay, so if you look at this graph, when the extension is negative, it's compressed. When the extension is positive, it's when we stretch the graph. Okay, so stretch. Ta-da! We assume that it is the same lah, although it is rarely the same. Okay, so this one is the W, energy stored in the material. So once again, one side must be extension, one side must be something that is related to the force. So you can see the red line is the thing that is related to the force. Okay, and then the other side is extension. So this is actually the energy stored, ladies and gentlemen, boys and girls. Okay. So again, all the prefixes, don't forget, don't mess up like me just now, or mess up like me and then make correction. So now we are going to replace it with a new rod. The new rod has double the Young modulus but 1/3 the area and the same original length. Okay, so you're asked to sketch the line on the graph from 0 to 90 kilonewton. So this is kind of like a very long-winded way to ask you where is the new compressed length for this new rod. 1/3 the area, 2 times the Young modulus. Okay, so let's say the change in length, I call it delta x prime. Okay, so number 1, you recall the Young modulus equation, which is stress over strain. Now, I use the symbol sigma over epsilon. Okay, so F over A, delta X over L. I'm just doing this again because it helps us remember. Alright, so step 1, we are going to recognize that the force applied is actually constant. Okay, and the original length is constant. Because what this question is asking you is that now I have the force of 90 kilonewton on this new wire, or this new metal, or this new material. What is the new extension? Given that this new material is 1/3 the area and twice the Young modulus. Okay, so all this kind of thing, right, is better to come up with the equation and find their relationship. And you can see since F and L naught is constant, or F and original length is constant, this allows us to arrive at a point where we can say or conclude that Young modulus is inversely proportional to A over del X. Okay, So if this is the case, you can, because it's inversely proportional, so 1, 2, go to the other side, 1 over becomes 2, 1 over 2, 1. Okay, so we just use ratio. So Young modulus is double, area is 1/3, but then you find the new extension for the same force, 90 kilonewton. So that's why it's not inside. So E over 2E is equal to new area over old area, new extension over old extension. Okay, so just rearrange and you will notice that our new extension is 3 millimeter. Okay, remember, my friends, in AS, ratio is your best friend. I repeat because this one need to repeat many times. Ratio is your best friend. So this inversely proportional, directly proportional, write out ratio thing is super important. You use it all the time, many chapters. Alright, so anyway, back to the question. Our new extension is 3 mm, so I'm going to zoom in and draw 3 mm. Remember, we are talking that the force is the same, 90 kilonewton. So the new extension is 3 mm, and we draw a line from the same original length, because it's the same original length, remember. Obey Hooke's law, so it has to be a straight line. So ta-da, that is your graph, and we are done. I will see you in the next video.